In this lecture, we are going to explain how we're going to make our neural net more wide and more deep. In our previous lectures, we introduced our linear model and logistic regression with one input x, and they will produce y hat based on our model. For example here, let's say we try to build HKUST PhD program application predictor. Applicants will submit their GPAs, and based on this input x, we're going to predict the y hat. Either she or he is going to be accepted or not. In our source code, we can express in our data like this. So each x will have only one value, like GPA here, and then y value is 0 or 1. However, if you can see this model, probably it's not really fair. Just using only one single input maybe does not have enough predictive power for our final result. So we need to introduce more input. So for example here, let's add one more input called experience. So in this case, it's not only we're gonna consider only GPAs, but also our model get the second variable, which is experience, as an input, and then we're gonna predict based on two inputs. In our x data can be expressed in this way. So now we have two data for each x. So how can I implement this one? So in order to implement this, we don't have to change our model. We just need to introduce matrix multiplication concept in our previous models, then everything works fine. So for example here, in our data set, x data can be expressed as a matrix. So here we do have n data, and then each data has a and b, two values. So we can express this one as a matrix with n by 2 matrix, and that's x. And then we do some w, xw, and then we'll produce our y. In this case, our y is also matrix with n. We have n data points with output. Each output is 1, so n by 1. And the question here is that which matrix we have to use to produce from this to this. We only need to decide this one, and then we set this linear model with that matrix. So in our case, it's very simple. So what we can do is that we can design our weights matrix with a 2 by 1, and they will produce this matrix. So basically we can see always this value should be the same, and then they will cancel out. Eventually they're gonna generate n by 1, so like this. So we just need a linear model with this matrix. Further generalize this model, not only 1 or 2, 3 inputs, we can have many inputs, and then we can just generalize this one as x as a matrix, and then w as also matrix will produce a matrix like this. In our case, because we have only two inputs, what we need is that we need the weights, which is linear model with a 2 by 1 matrix. So we can just, when we define our linear, we can say 2 by 1. Also, we can see this one as our x input has 2, so this is our input, and then our y input has only one output, so this one get 2 as an input, and then 1 produce 1 as an output. You can consider this one, and then you can design our linear model like this. So not only for 1 or 2, we can just make n types of inputs, and then we can make our model really wide. But not only wide, also we can make a little bit deep. So in previous example, we just only used one layer as our model, but it's not limited to make multiple layers. And to implement these multiple layers, basically what we need to do is that we just create multiple linear components in here, and then we just connect them together. One thing we need to be very careful is that what is the input size and then what is the output size. So this input size x is maybe let's say the input is 2, then the input first linear should be 2 by number, and then this will generate 4, and then second layer must get 4 as an input and produce any arbitrary number. But make sure the next layer, which get 3 as an input, and produce the last value, which in our case is y, is 1, so always this one should be 1. So in this example, always this value here is fixed. X is 2, y is 1. So this is fixed, but all the odd numbers in the middle, this can be arbitrary number. You make your decision. And then after we have these components, we just connect them all components together like using Sigmoid. And that's it. In our lecture, we use the Sigmoid as our activation function, which is simple and good enough. But when we build a very deep neural network, Sigmoid can cause a vanishing gradient problem. Basically, Sigmoid can squash values to a small number. So if you can multiply this small number, which is smaller than 1, then the number is getting smaller. So if you do backpropagation, we're gonna lose our gradients. So which is called the vanishing gradient problem. So there are many solutions to address this issue, but one simple way is that you can use other types of activation functions. Especially this ReLU works very well for this situation. So all these different types of activation functions are implemented there, so we can try different activation functions. If you want to more about the activation functions, you can visit this web page. And then you can select any activation functions, and then you can visualize this activation function with very nice explanations and equations. Using this deep and wide neural net, we can apply our model for real data sets like this, diabetes. So this data file is given as a CSV file. So the column is like this. So this is X data, and this is our prediction Y. For some test result, we can predict he or she might get the diabetes. So we just read everything using NumPy's utility function, and then get everything to XY. So this X can be XY, yeah, that everything, and from 0 to n-1 column, which can be expressed like 0 to -1. So like this. And then Y, we're gonna take only the last column, so which can be expressed something XY dot everything, and then the last column. So this is how we're gonna load X and Y, and then we can just transform this NumPy to Torch, and then we wrap the variable, and then we're gonna have X and Y data. And then if you want, you can just print out this, the shape of the data, and then we can see. So we have basically 759 data with 8 features, 8 X values, and then 1 Y value. And then we can just plug in everything using the same idea using class. Now what we want to do is that we want to make it a little bit wide. So here the input is 8, it's wide. And also we want to go deep, 3 layers. So when you design these components, the input is fixed, output Y is fixed. But in the middle, how many layers do you want to use? It's up to you. And then what's the output of each layer? It's also up to you. For example, here we just produce, for given 8 input, we're gonna produce 6 outputs. But this 6 output can be used for the second layers as input, like this. And then also this can produce 4, and then this can be used as an input for the last layer. And then we just connect these components in the right order, and then we're gonna use this sigmoid in our activation function. And that's it. And the entire source code looks something like this. So we're gonna load our data from CSV file, and then we just make X data and Y data. Make sure they are all PyTorch variable. And then we build our model using this class. And then our loss is same as BCE because it's 0 or 1 binary classification, and they use SGD. This is our loss and the optimizer, and then we run this training cycle. Basically we feed entire data, and then we feed entire data for the loss, and then after we computing the gradients, and then we just update our weights, and that's it. In our example, we just use 3 layers of the network, but it's not just limited with 3 layers. You can go 6, 7, 8, 10 layers. You can try out. Also, using exactly the same deep neural nets, we can try with other classification problems. In our example, we just used sigmoid activation function, but especially once you design deep neural nets, probably you can choose other activation functions. You can try with other activation functions. In our next lecture, we're gonna talk about how we're gonna make our data loading like much easier using data loader in the PyTorch.